Hello there, and welcome to the Sleepy Library. It's lovely to have you here. Before we begin our gentle journey to the Red Planet tonight, I'd love to know, where in the world are you watching from? A quiet bedroom with the curtains drawn? A peaceful corner where the day has finally settled down? Perhaps you're nestled under soft blankets, feeling their weight pressing gently against you. Or sitting in a comfortable chair with the lights dimmed low, creating shadows that dance softly on the walls. Maybe you're on a late-night train ride, watching darkness slide past the windows. Or in a cozy living room with a warm cup of tea cooling slowly on the table beside you. Wherever you are, whatever brings you to this video, I hope you're comfortable, warm, safe, and ready to let your thoughts wander slowly toward distant horizons, toward a world that has fascinated humanity for millennia. If you enjoy these relaxing explorations and would like to hear more, a like and subscribe really helps this sleepy little channel continue its cosmic wanderings. Your support allows us to keep creating these gentle journeys through science and space. These quiet explorations that prioritize understanding over urgency, curiosity over competition. And to those of you already subscribed, thank you. Truly, your support means more than you know. It's because of you that we can keep exploring the wonders of science together, one gentle video at a time, creating a space where learning and relaxation can coexist peacefully. Now, I'll try not to make tonight's topic so interesting that it keeps you wide awake. But if it does, at least you'll have a better understanding of humanity's most ambitious journey beyond our own world, of the persistent, patient, decades-long effort to understand our planetary neighbor. A fair trade for a restless night, I'd say. So, let's begin, shall we? Tonight, we're traveling to Mars, not in a spaceship, but in thought, following the gentle arc of human curiosity as it reaches across millions upon millions of kilometers of space to touch another world. We'll move slowly, softly, allowing each story to unfold at its own pace, giving each discovery the time and attention it deserves. There's no rush. Mars has been waiting for billions of years. It can wait a little longer for us to truly appreciate its mysteries, to understand the patient work that has revealed its secrets bit by bit. Mars has captivated humans for thousands of years, long before we knew what it was, long before we understood that it was a world like our own, long before we had telescopes or spacecraft, long before we even understood what planets were, or that they were worlds we might someday visit. That reddish point of light in the night sky held a special place in human imagination. Ancient Babylonians tracked its movements across the heavens 4,000 years ago, noting with careful attention how it seemed to wander among the fixed stars with a peculiar rhythm. Sometimes moving forward through the constellations, sometimes appearing to move backward in what we now call retrograde motion. They kept careful records, marking its positions relative to the stars, noting when it was bright and when it was dim, when it moved quickly and when it seemed to slow. These ancient astronomers didn't know they were observing the relative motions of two planets orbiting the Sun, but they knew they were seeing something important, something worth recording and studying. The ancient Egyptians called it Her Desher, the Red One, and associated it with the god Horus of the horizon, the sky god whose eyes were the sun and moon. They too tracked its movements, incorporating them into their calendar systems and religious observances. The Greeks named it after Ares, their god of battle and warfare, perhaps because its blood-red color reminded them of conflict and the aftermath of combat, of battlefields stained with blood. When the Romans adopted the planet into their cosmology, they renamed it Mars, after their own warrior deity, the father of Romulus and Remus, the protector of Rome. This is the name that has endured into our modern age, carried forward through medieval astronomy, through the Renaissance, through the telescope age, and into our current era of robotic exploration. That ruddy color, like rust or desert sand or the clay of ancient pottery, like brick dust or dried blood or autumn leaves, gave Mars an otherworldly quality that set it apart from the other wandering lights in the sky. While Venus shone brilliant white like a diamond, Jupiter glowed steady and golden like a distant lantern, and Saturn appeared pale yellowish like old parchment. Mars stood out with its distinctive reddish hue, a color that spoke of mystery and otherness, of fire and forge, of something fundamentally different from the cool blues and greens of Earth, or the pure brilliance of Venus. But Mars isn't just a point of light anymore. It isn't merely a wandering star whose position ancient astronomers meticulously recorded. Over the past 6 decades, spanning lifetimes, we've sent dozens of robotic explorers to visit this neighboring world, each one a messenger carrying our questions across the vast emptiness between planets. Some have flown past, snapping pictures as they zoomed by at incredible speeds, glimpsing Mars for just minutes before continuing into the outer solar system, or falling into orbit around the Sun. Others have slipped into orbit around Mars itself, circling the planet year after year, orbit after orbit, mapping every crater and canyon with patient precision, watching seasons change, monitoring dust storms that can engulf the entire planet, observing frost forming and sublimating at the poles. And a precious few, the ones we remember most fondly, have landed gently on the surface after their terrifying descents through the thin atmosphere, rolled across the rusty plains on wheels or tracks, drilled into ancient rocks, diamond-tipped bits, and sent back stories of a world that was once very different from the cold, dry desert we see today. Each mission has been a letter written across the void, a message of curiosity sent from one world to another, asking questions that have echoed in human hearts since our ancestors first looked up at the night sky and wondered what those wandering lights might be. Each spacecraft, whether it succeeded gloriously or failed quietly in the darkness, has taught us something, has added another piece to the puzzle, has brought us one step closer to understanding this neighboring world that is simultaneously familiar and utterly alien. Tonight, we'll drift through these stories together, one mission at a time, one discovery at a time, moving chronologically through the decades, from the first fumbling attempts to the sophisticated robots currently exploring the Martian surface. There's no hurry. Time moves differently when we're exploring the cosmos. The universe operates on timescales that dwarf human lifetimes. And while our individual lives are brief, our collective efforts span generations. We'll move slowly, gently, like a rover rolling across the Martian plains at a leisurely walking pace, stopping frequently to examine interesting features, to take photographs, to simply pause and appreciate the strangeness and beauty of being, in spirit, if not in body, on another world. We'll meet the spacecraft that succeeded beyond all expectations, operating for years beyond their planned lifetimes, and the ones that fell silent in the darkness of space after teaching us painful but necessary lessons about spacecraft design and the unforgiving nature of interplanetary travel. We'll explore ancient riverbeds that once carried rushing water under skies that were thicker and perhaps bluer than the butterscotch-tinged heavens of modern Mars. We'll stand at the rim of towering volcanoes that dwarf any mountain on Earth. Volcanoes so massive they distort the planet's shape. Volcanoes that may have erupted as recently as 25 million years ago, which in geological terms is yesterday. We'll peer into vast canyons that could swallow entire mountain ranges, canyons that stretch for thousands of kilometers along the Martian equator. Canyons so deep that if you stood at the bottom and looked up, the rim would be beyond the curve of the planet. We'll listen to the sounds of wind on another world, sounds that traveled across millions of kilometers of space, encoded in radio waves, translated back into sound waves so that human ears could hear the sigh of Martian breezes sliding past the rover's instruments. And we'll witness a helicopter take flight in an atmosphere so thin it shouldn't have been possible. A tiny machine with blades spinning at thousands of rotations per minute, proving once again that human ingenuity can accomplish things that seem impossible until someone actually does them, until theory becomes reality and dreams become achievements. So settle in, take a deep breath, letting it fill your lungs completely, then releasing it slowly, feeling tension drain away with the exhaled air. Let the concerns of the day gently release their hold on you. Whatever worries you brought with you to this video, whatever stress or anxiety has been your companion today, allow it to settle like dust after a storm, no longer swirling, just resting quietly. Close your eyes if you'd like, or keep them softly focused on these words: reading without urgency, absorbing without strain. Either way, allow yourself to be carried along on this journey, to be transported not through space, but through story, to visit Mars through the patient work of generations of scientists and engineers who devoted their careers to understanding this distant world. And let's begin our exploration of Mars, a place that teaches us not just about another planet, but about persistence, patience, ingenuity, and the quiet courage it takes to reach toward the unknown. A place that shows us that even our failures can be stepping stones to success, that even silence from across the void can teach us how to speak more clearly the next time we try. A place that reminds us that the universe is vast and mysterious and infinitely patient, and that understanding it requires not just brilliant insights, but steady, sustained effort across decades and centuries. In the early 1960s, as humanity was just beginning to peak beyond Earth's protective embrace, as we were learning the basics of spaceflight and orbital mechanics, as we were figuring out how to keep humans alive in the vacuum of space and how to navigate beyond our planet's gravity well, Mars beckoned with an irresistible pull. The planet had always fascinated us, but now, for the first time in human history, we had the technology to actually go there, to send machines across the gulf of space and see Mars up close, rather than as a distant point of light through telescopes. The Soviet Union, fresh from its triumph of putting the first human in space, from Yuri Gagarin's historic orbit in April 1961 that had captured the world's imagination, made the first attempts to reach the Red Planet in 1960. Two spacecraft, optimistically designated Mars 1960A and Mars 1960B, were prepared for their historic journey. Engineers worked long hours in the cold halls of Soviet design bureaus, checking and rechecking systems, calculating trajectories with slide rules, and early computers that filled entire rooms with vacuum tubes and magnetic tape, preparing these mechanical emissaries for a journey that would take them farther from Earth than any human-made object had traveled before. But space travel, it turns out, is not forgiving of even the smallest mistakes. The vacuum of space magnifies errors, and the vast distances involved leave no room for rescue missions or second chances. A flaw that would be trivial on Earth can be catastrophic in space. A tiny seal that leaks, a circuit that overheats, a guidance system that drifts by a fraction of a degree can spell the difference between success and failure. Both spacecraft failed to leave Earth's orbit, their rocket stages malfunctioning in ways that would be analyzed for months afterward. Engineers poring over telemetry data, trying to understand exactly what went wrong so they could prevent the same failure next time. The third-stage engines that should have fired to send them toward Mars simply didn't ignite properly, or didn't burn long enough, or misfired in some subtle way that left the spacecraft stranded in Earth orbit rather than arcing outward toward Mars. The mission ended before it truly began, with both spacecraft eventually tumbling back into Earth's atmosphere and burning up over the Pacific Ocean, bright meteors containing all the hopes and efforts of thousands of people. But humanity didn't give up. We never do, really. That's perhaps one of our most defining characteristics as a species. When we fail, we learn, we adjust, we try again. We pick ourselves up, examine what went wrong, make changes, and try once more. And again. This persistence, this refusal to accept defeat, this determination to keep reaching toward our goals, no matter how many setbacks we encounter, is part of what makes us human. Between 1960 and 1969, spanning nearly a decade of dedicated effort, the Soviet Union launched 9 different probes toward Mars. 9 separate attempts, each one representing years of planning, months of construction, countless hours of testing in vacuum chambers and centrifuges and thermal chambers, and the hopes of thousands of engineers, scientists, and dreamers who believed that reaching another world was not just possible, but necessary. Not just a technical achievement, but a human imperative. Each one carried hopes and dreams. Each one represented countless hours of planning and preparation, countless nights of engineers solving problems and testing systems, countless calculations and simulations and tests. And each one, in its own way, fell short of its goals, teaching lessons but not achieving its mission. Some failed at launch, the rockets breaking apart in spectacular fireballs, visible for kilometers around the launch site, or simply refusing to light their engines, sitting silent on the pad as launch windows closed and Mars moved on in its orbit. Others made it into space, but couldn't sustain their journey, falling victim to communication failures when antennas failed to deploy or transmitters burned out, guidance system problems that sent them spinning off course, or simple mechanical breakdowns in the harsh environment of space where metal contracts in the cold and lubricants freeze, and solar panels must work perfectly or everything shuts down. Mars 1, launched in November 1962, actually began the long voyage toward the Red Planet, faithfully transmitting data about the plane's empty reaches between worlds, sending back measurements of radiation levels and cosmic rays and the solar wind, contributing to our understanding of interplanetary space, even as it failed in its primary mission. Engineers listened to its signals, plotted its trajectory, and prepared for the encounter with Mars. But then, when it was about 107 million kilometers from Earth, roughly 2/3 of the way to Mars, when the engineers were beginning to prepare the commands for its encounter with the Red Planet, communication ceased. The signals stopped arriving at the tracking stations. The spacecraft tumbled silently onward, carrying its instruments and cameras past Mars, without ever being able to share what it might have seen, without being able to complete the mission for which it was built. Perhaps a micrometeorite punctured a fuel line. Perhaps a circuit failed from radiation exposure. Perhaps the spacecraft simply got too cold in the endless shadow of interplanetary space. We'll never know exactly what happened, and that's part of the challenge of space exploration. When something goes wrong millions of kilometers away, there's no way to send a repair crew, no way to examine the wreckage, no way to know for certain what failed. These early failures might seem discouraging, and indeed they were to the people who worked on these missions, who saw years of their lives invested in spacecraft that never completed their objectives. But there's something quietly beautiful about them too, something admirable in the sheer persistence, in the willingness to try again after each failure. Each attempt taught engineers something new about the challenges of interplanetary travel, about the harsh realities of space, about what works and what doesn't. Each failure was a teacher, patient and thorough, showing exactly where designs needed to improve, where calculations needed refining, where redundancies needed adding, where materials needed strengthening. The journey to Mars was paved with these lessons, each one purchased at the cost of years of work and millions of rubles and dollars, each one making the next attempt slightly better, slightly more likely to succeed. America's first attempt came in 1964 with Mariner 3, as NASA joined the race to explore Mars. Launched on November 5th, it carried sophisticated cameras designed to photograph Mars during a flyby. Cameras that could resolve features smaller than any telescope on Earth could see, that would reveal Mars in unprecedented detail. But something went wrong with the protective shroud that covered the spacecraft during launch. The aerodynamic shell designed to protect the delicate instruments as the rocket climbed through Earth's atmosphere. The shroud was supposed to fall away once the craft was in space, once it was beyond the atmosphere where aerodynamics no longer mattered. But it didn't. It stayed attached, encasing the spacecraft like a tomb, blocking the solar panels from the sun's light. Without power from those panels, without the electricity they were supposed to generate from sunlight, the spacecraft's batteries slowly drained over hours and days, and Mariner 3 went silent, another quiet voice lost in the cosmic dark. Another lesson learned about the hundreds of things that must go right for a mission to succeed. 3 weeks later, America tried again, demonstrating the same persistence that the Soviet Union had shown. Mariner 4 launched on November 28, 1964, carrying identical instruments and a similar mission profile. Engineers had analyzed what went wrong with Mariner 3, had identified the problem with the shroud, had redesigned that crucial component. But this time, everything worked. The rocket performed flawlessly. The shroud separated properly, falling away and allowing the spacecraft to spread its solar panels like wings. And 9 months later, after a journey of 228 days across nearly 500 million kilometers of space, coasting on the trajectory imparted by its launch rocket, making tiny course corrections with small thruster firings. On July 14, 1965, Mariner 4 made history. It was the first spacecraft to successfully fly by Mars and return close-up images. The first time humanity had seen another planet up close, rather than as a distant blur through telescopes. The journey took 228 days across nearly 500 million kilometers of space, most of it spent in silence, with just occasional check-ins to verify the spacecraft was still functioning, still on course. And when it finally swept past Mars at a distance of just under 10,000 kilometers, close enough to see surface features clearly, but far enough to be safe from any possibility of collision, traveling at more than 7 kilometers per second relative to Mars, its cameras began clicking, capturing images on a strip of film that would be scanned and transmitted back to Earth bit by bit, over the following days and weeks. 22 pictures in total were captured over a span of about 25 minutes, as the spacecraft hurtled past, each image carefully timed, each precious given the limitations of the camera system and the amount of film available. 22 images that would revolutionize our understanding of Mars, that would shatter centuries of speculation and replace it with hard data. But here's a charming detail about that historic moment, a human touch in this story of technological achievement. The images were transmitted back to Earth as strings of numbers, digital data representing different brightnesses across the picture, each pixel encoded as a number that indicated how much light the camera had detected at that point. This was state-of-the-art technology in 1965, but it meant the images existed first as data, not as pictures. And the mission team, eager to see what Mars looked like up close, eager to see the fruits of their years of labor, couldn't wait for the computers to slowly process these numbers into viewable images. The computers of that era were slow by modern standards, and processing an image could take hours. So they did something wonderfully analog, something charmingly human. They printed out the numerical data on strips of paper, long ribbons of numbers emerging from the printer, and then, with colored pencils in hand, they hand-colored each number according to its brightness value, like a paint-by-numbers kit, but with data from another planet. Dark numbers got dark colors, browns and blacks. Light numbers got light colors, tans and whites. And slowly, stroke by stroke, pencil marking by pencil marking, the first close-up image of Mars emerged under their hands, appearing on paper through human effort, before it appeared on any computer screen. That first image showed Mars's curved horizon against the blackness of space, a simple but profound sight. The edge of another world, the boundary between rock and void, between atmosphere and emptiness. Simple, elegant, beautiful in its starkness. A reminder that even our most sophisticated technological achievements are accomplished by human hands and human patience, by people who care deeply about what they're doing, who can't wait to see the results, who will grab colored pencils if that's what it takes to see an image sooner. The other 21 images revealed something that surprised everyone, that challenged decades of speculation about Mars. Mars wasn't covered with canals or cities or vegetation, as some had hoped and some had claimed to observe through telescopes. Giovanni Schiaparelli had described channels, which were mistranslated as canals, leading Percival Lowell and others to propose elaborate theories about Martian civilizations building waterworks to survive on a drying planet. But Mariner 4's images showed none of that. Instead, Mars was cratered, heavily pitted with impact scars like Earth's moon, showing a surface that had been bombarded by asteroids and comets over billions of years. Ancient, cold, seemingly lifeless, desolate in a way that challenged romantic notions of a living Mars. Those images dispelled centuries of speculation about Martian civilizations in a few grainy black and white frames, replacing imagination with observation, speculation with data. But far from diminishing our interest in Mars, those first images deepened it, raising new questions even as they answered old ones. Because if Mars was ancient and cratered, if it had been shaped by asteroid impacts over billions of years, without the resurfacing that happens on geologically active worlds, then perhaps its surface held secrets about the early solar system, about the era of heavy bombardment when asteroids and comets careened through the inner solar system like cosmic pinballs. Perhaps beneath that dusty exterior lay clues about how planets form, how they evolve, whether they follow similar paths or diverge based on subtle differences in their formation. And the craters themselves told stories, each one a moment of violence frozen in stone, each one a clock that geologists could read to estimate the age of the surface. After Mariner 4's success, NASA sent 2 more spacecraft toward Mars, building on what they'd learned, refining the technology, planning more ambitious observations. Mariner 6 and Mariner 7 launched in February and March of 1969, just months after Apollo 8 had carried humans around the Moon, in an era when space exploration was accelerating rapidly, when new achievements seemed to come monthly. The 2 spacecraft arrived at Mars in late July and early August, timing their arrivals carefully to observe different parts of the planet. Together, they returned over 200 images, greatly expanding our understanding of the Martian surface, filling in details, showing regions Mariner 4 hadn't seen. They photographed the polar ice caps in detail, revealing layers and textures that hinted at seasonal changes, at annual cycles of freezing and sublimating, at a dynamic process rather than static ice. They captured images of the southern hemisphere, showing more ancient terrain, more craters, and still no signs of the elaborate canal systems that early telescopic observers thought they'd seen, that Percival Lowell had mapped and given names to, that had inspired H.G. Wells to write The War of the Worlds, and Edgar Rice Burroughs to set adventures on Barsoom. The canals, it turned out, were optical illusions, the human eye connecting random features into patterns that seemed to have meaning but didn't really exist. These flyby missions were technological marvels in their own right, achievements that still impress today. Imagine sending a spacecraft to a planet that's tens of millions of kilometers away, that's moving through space at nearly 25 kilometers per second, arriving months later, exactly when and where you planned, having navigated across the solar system with only a few small course corrections, then having just minutes to capture as many images and measurements as possible before speeding past into the darkness beyond, into an orbit around the Sun that would never bring you near Mars again. It's like trying to photograph specific landmarks from a speeding train, except the train is traveling through the vacuum of space at thousands of kilometers per hour. The landmarks are on a planet millions of kilometers away, and you only get one chance, one brief window when everything must work perfectly, or years of effort are wasted. But flybys, however impressive, however much they taught us, could only tell us so much. You can learn a lot from a photograph taken while speeding past, but there's so much more you could learn if you could slow down, stop, stay a while. What Mars really needed was a spacecraft that would slow down as it approached rather than flying past, settle into orbit using rocket engines to brake against the orbital velocity, and stay there, patiently watching, mapping, and studying the planet over months and years. An orbiter would see how Mars changed with seasons, could map the entire surface rather than just the swathe visible during a flyby, could study the atmosphere and polar caps in detail. The race was on to build an orbiter, to be the first to not just visit Mars, but to stay there, to become, in a sense, a temporary moon of the red planet. In 1971, both the Soviet Union and the United States sent spacecraft toward Mars, each hoping to be the first to orbit another planet, each hoping to claim another first in the space race that had driven so much of early planetary exploration. The Soviets launched 3 missions, Mars 2, Mars 3, and a spacecraft that failed shortly after liftoff, never even receiving a proper designation. America launched Mariner 9. What happened next was both a triumph and a lesson in the unpredictability of Mars, a reminder that even when we plan everything carefully, even when our engineering is sound, nature can still surprise us. When the spacecraft began arriving at Mars in November 1971, converging on the planet from their separate trajectories, They found the planet completely obscured by a massive dust storm, one of the planet-wide dust storms that occasionally engulf Mars. Imagine traveling for months across interplanetary space, through the vast emptiness, watching Mars grow slowly from a point of light to a visible disk, anticipating the discoveries to come, finally reaching your destination, only to find that the entire planet was wrapped in a thick, swirling blanket of dust. Nothing on the surface was visible. No features could be discerned. It was like arriving at a museum, only to find all the exhibits covered in sheets, or traveling to a spectacular vista, only to arrive in thick fog. The Soviet spacecraft, programmed to begin photographing Mars immediately upon arrival, following instructions uploaded before launch and not easily changed, did exactly that. They took pictures of dust, just dust. Thick, featureless, tan-colored dust extending in every direction, from horizon to horizon. No craters, no volcanoes, no canyons, just the swirling upper atmosphere filled with suspended particles. Their programming didn't allow for much flexibility, couldn't adapt to changing conditions. They followed their instructions, and those instructions assumed Mars would be visible, assumed clear skies, assumed the observations could begin immediately. It was a limitation of 1970s technology, when spacecraft couldn't be reprogrammed easily, when instructions were burned into their computers and couldn't be changed. But Mariner 9, arriving slightly later, had a different fate, because it had more flexibility in its programming, and because the NASA team made a crucial decision. Seeing the dust storm still raging, understanding that photographing dust would waste precious film, they made a choice. They would wait. They programmed the spacecraft to remain in orbit, conserving film and power, simply watching and waiting for the dust to settle, monitoring the storm, tracking its evolution. It was a decision that required patience, that required trusting that the storm would eventually end, that the wait would be worth it. And slowly, over the following weeks, as mission controllers watched and hoped, as days turned into weeks, the dust did settle, the atmosphere gradually clearing as particles drifted back down to the surface. As the dust began to clear, filtering down slowly, the first features to emerge were unexpected and mysterious. 4 dark spots appeared, rising above the dusty haze, visible even while the surface was still obscured. These weren't craters or plains, or any feature anyone had expected to see first. They were mountain peaks so tall they poked through the upper layers of the dust storm, rising above the bulk of the atmosphere. They were the summits of Mars's enormous volcanoes, including Olympus Mons, which would turn out to be the largest volcano in the entire solar system. A mountain so massive it dwarfs anything on Earth, so tall it rises above much of the Martian atmosphere. Once the air cleared completely, once the dust had settled and Mars was visible again, Mariner 9 began its work in earnest, and what it revealed was astonishing, far beyond what anyone had anticipated. Mars wasn't just a cratered moonscape, wasn't just a dead world peppered with impact scars. It was a world of incredible geological diversity, with features on a scale that made Earth's geology seem modest. There were enormous volcanoes, yes, but there were also vast canyons, channels that looked like dried riverbeds carved by catastrophic floods, layered terrain suggesting ancient sedimentary processes where particles had settled out of water or air over long periods, and polar caps that changed with the seasons, growing and shrinking as carbon dioxide froze and sublimated. The spacecraft mapped about 85% of the Martian surface, meticulously photographing region after region, building up a comprehensive picture of the planet's geography. It returned over 7,000 images, each one adding details, each one revealing new surprises. It discovered Valles Marineris, a canyon system so vast it makes Earth's Grand Canyon look modest by comparison, look like a small scratch on the surface. This feature stretches for more than 4,000 kilometers along Mars's equator, about the length of the entire United States from coast to coast, a distance you could drive for days without seeing both ends. In places, it's 200 kilometers wide and 7 kilometers deep. If you stood on one rim and looked across to the other side, it would be beyond the horizon, lost in the curve of the planet. You couldn't see the opposite wall even on the clearest day, because it would be hidden by Mars's curvature. Mariner 9 also found ancient river valleys, sinuous channels that meandered across the ancient highlands exactly like rivers on Earth, suggesting that water had once flowed across the Martian surface in great quantities, carving channels through rock, transporting sediment, perhaps supporting life. This was revolutionary, a complete change in how we thought about Mars. Water means the possibility of life, at least as we know it. Water means chemistry can happen, means complex molecules can form, means conditions might have been right for biology. Water also requires a thicker atmosphere and warmer temperatures than Mars currently has, requires greenhouse gases to trap heat, requires conditions very different from the cold, thin-aired Mars we see today. So if water once flowed there, Mars must have changed dramatically over its history, must have gone through massive climate shifts. The planet had a story, a history of transformation, and we were just beginning to read it, just starting to piece together the narrative of how Mars changed from a warmer, wetter world into the frozen desert it is today. By the mid-1970s, after the success of Mariner 9, after the discovery of ancient water channels and enormous volcanoes, NASA was ready for its most ambitious Mars mission yet. Not just orbiters circling overhead, but landers that would actually touch down on the surface. Not just cameras looking at Mars from a distance, but laboratories that would scoop up soil and analyze it, instruments that would taste the Martian air, experiments that would search for life itself. Not just mapping Mars, but actively searching for biology, trying to answer the ancient question of whether we are alone. The Viking program consisted of 2 identical spacecraft, each with an orbiter and a lander, redundancy built in, so that if one failed, the other might succeed. Viking 1 launched in August 1975, followed by Viking 2 in September. Both arrived at Mars in 1976, America's bicentennial year, a year of national celebration that would include humanity's first successful Mars landing. The landings themselves were nerve-wracking achievements, each one a carefully choreographed sequence that had to work perfectly. Each lander separated from its orbiter high above Mars, beginning a descent that would take it from the safety of orbit to the surface in a matter of minutes. The lander plunged into the thin Martian atmosphere, friction heating its heat shield to thousands of degrees, slowing from orbital velocity through atmospheric drag. Then it deployed a parachute to slow its descent further, the huge chute billowing above it. Finally, as it neared the surface, it fired retro rockets to cushion its touchdown, hovering on rocket thrust for the final moments before settling gently onto the surface. It was the first time any spacecraft had successfully landed on Mars and operated there, and both Viking landers succeeded beautifully, touching down safely and beginning operations immediately. Viking 1 touched down in Kreis-Planitia on July 20, 1976, setting down in what appeared from orbit to be a relatively smooth plane. The first color image it sent back showed a rocky plain under a butterscotch-colored sky, a view that would become iconic, that would be reproduced in textbooks and documentaries, that would shape how people imagined Mars. The ground was reddish-orange, covered in rocks and fine dust, looking somewhat like a desert on Earth, but clearly alien, clearly somewhere else. The sky was tan, tinged with the dust that constantly hangs in the thin Martian air, rust particles suspended in the atmosphere, giving the sky its distinctive color. It looked alien and familiar at the same time, a desert under a strange sky, a landscape that could almost be Earth, but clearly wasn't. Viking 2 landed 2 months later in Utopia Planitia, further north and at a slightly higher latitude, in a region that appeared different from Chryse in the orbital images. Together, the two landers operated for several years, far exceeding their planned 90-day missions, continuing to function through multiple Martian seasons. Viking 1 sent its last transmission in November 1982, over 6 years after landing, after hundreds of Martian sols during which it measured, photographed, and analyzed its surroundings. Viking 2 lasted until April 1980, nearly 4 years after touching down. These extended missions were possible because the landers were powered by radioisotope thermoelectric generators rather than solar panels, so they didn't depend on keeping solar panels clean or having sufficient sunlight. What did they do during all that time, during those thousands of sols? They took pictures, thousands and thousands of them, showing the Martian surface in exquisite detail. They showed rocks of various sizes and shapes, sand dunes forming and shifting, morning frost sublimating as the sun rose, dust devils dancing across the plains. They measured the weather, tracking temperatures, wind speeds, and atmospheric pressure as Mars orbited the Sun and seasons changed, building up a comprehensive picture of Martian meteorology. They found that temperatures could vary by over 100 degrees between day and night, that winds were generally light but could sometimes gust strongly enough to lift dust, that pressure changed with the seasons as carbon dioxide froze and sublimated at the poles. They scooped up Martian soil and analyzed its chemical composition, finding a surface rich in iron oxide, which explains the rust-red color we see from Earth, a surface that had been oxidized over billions of years. But the most important and most controversial experiments were the ones designed to search for life, the ones that made Viking truly revolutionary. Each lander carried 3 biological experiments intended to detect signs of living organisms in the Martian soil, to answer the question that had driven exploration since Schiaparelli first described channels. The experiments added nutrients to soil samples and looked for signs of metabolism, growth, or respiration, for the chemical signatures of life processes. The experiments were cleverly designed, based on what we knew about life on Earth, on the assumption that Martian life, if it existed, would have similar basic chemistry. The results were puzzling and remain controversial to this day. Some experiments gave positive results, suggesting something active in the soil, something that was consuming nutrients and producing gases in patterns that looked biological. But other tests showed no organic molecules, none of the carbon-based compounds that we associate with life, that we assume must be present for biology to exist. The scientific consensus eventually settled on the conclusion that the positive results were likely due to unusual chemistry in the Martian soil, not biology. Perhaps perchlorates in the soil were reacting with the nutrients, producing the observed patterns. Mars appeared to be sterile, at least at the 2 landing sites tested, at least based on the instruments Viking carried. And yet, the question remained open, unsettled, inviting further exploration. The Viking landers could only sample the top few centimeters of soil in 2 small areas on a planet with the land area of all Earth's continents combined. They examined 2 spots on a world with almost the same land area as Earth, 2 tiny samples from an entire planet. Absence of evidence, as the saying goes, isn't evidence of absence. Just because Viking didn't find life doesn't mean life never existed on Mars, or doesn't exist elsewhere on the planet. The question of life on Mars would require more exploration, more sites, more sophisticated instruments capable of detecting subtler biosignatures. The Viking orbiters, meanwhile, continued photographing Mars from above, filling in details that Mariner 9 had missed, discovering new features, and creating maps of unprecedented resolution. Together, the Viking orbiters and landers revolutionized our understanding of Mars, transforming it from a mysterious red dot into a real place, with landscapes and weather and chemistry we could begin to understand. A place that became less alien and more familiar, even as it remained profoundly different from Earth. After Viking, there was a long gap in successful Mars exploration, a pause of nearly 2 decades during which no new spacecraft successfully reached Mars. The Soviet Union tried again in 1988 with Phobos 1 and Phobos 2, missions designed to study Mars's larger moon, Phobos, a mysterious potato-shaped satellite that might be a captured asteroid. Contact with Phobos 1 was lost on the way to Mars due to a simple command error, a reminder of how fragile these missions are. Phobos 2 made it into orbit, but failed just before it was supposed to drop landers onto Phobos's surface, tantalizingly close to success, but ultimately falling short. NASA launched Mars Observer in 1992, an ambitious mission to map Mars in detail and study its climate and geology with an advanced suite of instruments. But just 3 days before it was supposed to enter orbit, in August 1993, just as success seemed assured, contact was lost. The spacecraft simply stopped transmitting. The most likely explanation was a fuel tank rupture during the pressurization sequence before the orbital insertion burn, a catastrophic failure that probably destroyed the spacecraft. But the exact cause remained a mystery, adding to the list of Mars missions that ended in silence. The spacecraft, representing years of work and hundreds of millions of dollars, simply went quiet and was never heard from again. These failures were painful, demoralizing for the teams that worked on them, frustrating for a scientific community eager to continue exploring Mars. But they taught important lessons about spacecraft design, mission architecture, and the need for redundant systems. In response to the high costs and high-profile failures, NASA began emphasizing a new philosophy called faster, better, cheaper. The idea was to build smaller, less expensive spacecraft on shorter timelines, accepting that some might fail, but hoping that the increased pace of missions would lead to more overall success. Instead of building massive flagship missions that took a decade to develop and cost billions, NASA would build smaller missions that could be developed in a few years for a few $100 million. Mars Global Surveyor, launched in November 1996, embodied this new approach and succeeded wonderfully, demonstrating that the new philosophy could work. It reached Mars in September 1997 and spent nearly a decade in orbit, mapping the planet with unprecedented precision, far surpassing even Viking in the detail and coverage of its observations. Its laser altimeter measured elevation across Mars's entire surface, bouncing laser pulses off the ground and measuring the return time to determine height with meter-scale precision. Those measurements showed that Olympus Mons rises 22 kilometers above the surrounding plains, making it 2.5 times taller than Mount Everest. The data revealed the full scale of Valles Marineris, showed the subtle terrain variations across the planet, identified volcanic features and ancient lake beds. The spacecraft also revealed evidence that liquid water might have flowed on Mars in the geologically recent past, perhaps even within the last million years. This was based on images showing gullies on crater walls that looked remarkably fresh, with features suggesting they were carved by flowing water, possibly seasonal melting of frost deposits. If water flowed recently, perhaps it could flow again under the right conditions. Perhaps. Mars wasn't quite as unchanging as it seemed. Perhaps there were still processes happening today that could involve liquid water in limited circumstances. While Mars Global Surveyor mapped from orbit, circling the planet every couple of hours, another spacecraft took a different approach, demonstrating a new landing technology. Mars Pathfinder, launched in December 1996, was designed to demonstrate new landing technology and deploy the first rover to another planet, proving that mobile exploration was possible. On July 4, 1997, Pathfinder arrived at Mars in dramatic fashion. Instead of using retro rockets for a soft landing like Viking, which required complex, heavy systems, it bounced. The spacecraft was encased in airbags, like giant beach balls surrounding the lander, and after its parachute slowed the descent through most of the atmosphere, it simply hit the ground at high speed, bounced like a beach ball multiple times, perhaps 30 or 40 meters high, rolled to a stop, deflated the airbags, and opened like a flower, deploying solar panels and releasing its tiny rover. The rover was named Sojourner, after Sojourner Truth, the 19th century abolitionist and women's rights activist who fought for justice and equality. Sojourner, the rover, was small, about the size of a microwave oven, with 6 wheels and a top speed of about 1 centimeter per second, slower than a snail's pace. It was designed to operate for 7 days and travel no more than 10 meters from the lander, to demonstrate the concept and conduct a few basic experiments. It exceeded all expectations, as rovers so often do. Sojourner operated for nearly 3 months, traveling a total of just over 100 meters, but capturing the world's imagination in the process. People around the world followed the rover's progress, logging onto NASA's website in such numbers that it crashed repeatedly, everyone wanting to see the latest images from Mars. It used an instrument called an alpha-proton X-ray spectrometer to analyze the chemical composition of Martian rocks and soil, pressing the instrument against rocks and waiting patiently while it bombarded them with radiation and measured what came back. It took pictures with its tiny cameras. It navigated around obstacles using a simple but effective autonomous system that allowed it to avoid getting stuck. But perhaps more importantly, Sojourner proved that rovers could work on Mars, that the concept was sound. It demonstrated that we could build a mobile robot, land it on another planet, and drive it around reliably, dealing with the communications delay, with the unpredictability of terrain, with the harsh environment. That proof of concept paved the way for much larger, more capable rovers that would follow in the coming decades. Rovers that would transform our understanding of Mars. The lander, meanwhile, took thousands of images of the landing site, monitored the weather with simple instruments, and analyzed the composition of dust particles hanging in the atmosphere. Together, lander and rover showed that the rocks in the landing site had been rounded by water, suggesting an ancient flooded environment, perhaps the outflow from catastrophic floods that carved channels elsewhere on Mars. The discovery added to the growing evidence that Mars once had abundant liquid water, that it once had a very different climate. Pathfinder demonstrated that Mars exploration didn't have to be expensive to be effective. The entire mission, including development, launch, and operations, cost about $280 million, far less than Viking or Mars Observer. It was a validation of the faster, better, cheaper philosophy, and set the stage for an even more ambitious rover mission that would build on everything learned from Sojourner. In 2003, NASA launched twin rovers toward Mars, identical spacecraft heading to different landing sites. Named Spirit and Opportunity, they were identical six-wheeled vehicles, each about the size of a golf cart, much larger and more capable than Sojourner had been. They were designed to search for evidence of past water activity, to examine rocks and soil in detail, looking for minerals that form in water, for textures that indicate water processes. Their primary mission was planned for 90 days, with a goal of traveling a few hundred meters and examining several rock outcrops and soil samples before succumbing to dust buildup on their solar panels or mechanical failures. They did considerably better than that, so much better that they became legends of robotic exploration. Spirit landed on January 3, 2004, in Gusev crater, thought to be the site of an ancient lake, based on orbital images showing a channel draining into it. 3 weeks later, Opportunity landed on the opposite side of Mars in Meridiani Planum, a region showing signs of the mineral hematite from orbit, which often forms in water. Both landings used the same bouncing airbag system that had worked for Pathfinder, and both rovers rolled onto the Martian surface, ready to explore, ready to search for evidence of ancient water. Almost immediately, within days of landing, Opportunity found what the mission was looking for. Right at its landing site, exposed in the wall of a small crater the rover happened to land near, were rock layers showing clear evidence of having formed in standing water. The rocks had textures and compositions that could only form through interaction with liquid water over extended periods, showing the crossbedding that forms when sediments settle in moving water, showing the blueberries, tiny spheres of hematite that formed in water. Within weeks of landing, Opportunity had already achieved its main scientific goal, finding definitive proof that liquid water once existed on Mars's surface. But that was just the beginning of a journey that would last over 14 years. 14 years. Let that sink in for a moment. A rover, designed to last 90 days, operated for over 14 years, over 50 times its design lifetime. It traveled over 45 kilometers across the Martian surface, examined hundreds of rock formations, discovered meteorites lying on the surface like gifts, and peered into several craters, always searching, always learning, always finding new things. It found evidence of ancient environments where life could potentially have thrived, including acidic lakes and mineral-rich waters, environments that had the chemistry and energy sources that life needs. The rover survived dust storms that blacked out the sky, cleaned its solar panels when Martian winds happened to blow dust off them in fortunate cleaning events, and operated through multiple Martian winters, despite temperatures dropping far below what the electronics were designed to handle. Mission engineers developed clever strategies to keep it alive, including positioning it on sun-facing slopes during winter to maximize solar energy, and putting it into low-power modes during the coldest nights, turning off everything except the heaters that kept critical components from freezing. Spirit, meanwhile, was discovering different stories in Gusev crater. While the crater floor itself didn't show much evidence of water, appearing to be mostly volcanic plains, Spirit drove to nearby hills and found rocks that had clearly been altered by water, including minerals that only form in hot springs or volcanic steam vents. The rover climbed slopes that engineers thought might be too steep, examined rock outcrops that required careful positioning to reach, and sent back images of stunning panoramas showing distant crater rims and dust devils swirling across the plains like small tornadoes. Spirit's journey ended in 2010, when it became stuck in soft soil, a patch of ground that looked safe but turned out to hide fine, powdery material beneath a crust. Despite months of attempts to free it, despite careful experiments on Earth with duplicate rovers and simulated Martian soil, despite the dedication of engineers working every possible angle, the rover remained mired, unable to position its solar panels toward the sun as winter approached. It sent its last transmission on March 22, 2010, having operated for over 6 years and traveled 7.7 kilometers, having seen sunrise over 2,000 times on another world. Opportunity continued alone until June 2018, when a planet-wide dust storm darkened the skies above Mars, one of the massive storms that occasionally engulf the entire planet. The storm blocked so much sunlight that Opportunity's solar panels couldn't generate enough power to keep the batteries charged. The rover went into a low power mode, waiting for the dust to clear, essentially going to sleep to conserve its remaining energy. But when skies finally brightened months later, after the storm had dissipated and visibility returned, Opportunity never woke up. Perhaps dust had covered its solar panels too thickly, a layer too heavy for winds to remove. Perhaps the cold nights without power had permanently affected its batteries or electronics. Perhaps too many systems had failed during the long period of inactivity. We don't know exactly why, but on February 13th, 2019, after receiving no response to hundreds of communication attempts, after playing wake-up songs like David Bowie's Life on Mars to try to rouse it, NASA officially declared Opportunity's mission complete, saying goodbye to a rover that had become beloved around the world. Together, Spirit and Opportunity had revolutionized our understanding of ancient Mars. They proved that water had been widespread on the surface billions of years ago, not just in isolated areas, but across much of the planet. They showed that early Mars had diverse aqueous environments, some acidic, some neutral, some volcanic, each with different chemical conditions that might have been suitable for different types of life. And they demonstrated that rovers could operate for years in the harsh Martian environment, setting the stage for even more ambitious missions, for larger rovers with more sophisticated instruments. On November 26, 2011, NASA launched the Mars Science Laboratory mission, carrying the rover Curiosity, a name that perfectly captured the spirit of exploration. This was not a small rover like Spirit and Opportunity. Curiosity weighed about 900 kilograms, roughly the same as a small car, and stood about 2 meters tall at the top of its camera mast. It carried 17 cameras and a sophisticated suite of scientific instruments, including a laser for zapping rocks from a distance and analyzing the vaporized material, a drill for collecting samples from inside rocks, and a mobile laboratory capable of analyzing the chemistry and mineralogy of samples. It was powered by a radioisotope thermoelectric generator like Viking, so it didn't depend on sunlight and could operate anywhere on Mars, even in winter, even in shadowed areas. The landing was a nail-biting affair, an entirely new system never tried before. Curiosity was too heavy for airbags. Instead, NASA developed a new system called the Sky Crane, something that sounded like science fiction but worked perfectly in practice. After atmospheric entry and parachute deployment, the descent stage fired rockets to slow down and hover above the surface, then lowered Curiosity on cables like a giant crane, setting it gently on its wheels before flying away and crashing a safe distance away. It sounds impossible, like something that couldn't possibly work, but it did. On August 6, 2012, Curiosity rolled onto the floor of Gale Crater, ready to begin its mission. Gale Crater was chosen because at its center rises Mount Sharp, a layered mountain that represents billions of years of Martian history in its sedimentary rocks. By driving up the mountain and examining these layers, curiosity could essentially travel through time, studying how Mars changed from an early, warm, wet world into the cold, dry desert it is today. The mountain is like a history book, with each layer a chapter, each chapter telling part of the story of how Mars evolved. The rover's first major finding came quickly. In an area called Yellowknife Bay, Curiosity drilled into mudstone rocks and found evidence of an ancient riverbed and lakebed, where conditions were right for microbial life, had any existed. The water was neutral pH, not too acidic or alkaline, not too salty, and contained all the chemical elements necessary for life as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. For the first time, we had concrete evidence that Mars once had habitable environments, places where life could have thrived if it ever arose or arrived from elsewhere. As Curiosity climbed higher up Mount Sharp, it continued making discoveries that filled in details of Mars's history. It found organic molecules preserved in ancient rocks, showing that carbon-based chemistry existed on Mars billions of years ago, that the building blocks of life were present. It detected seasonal variations in atmospheric methane, the levels rising and falling with the Martian seasons, suggesting either active geology or perhaps biology somewhere on the planet releasing methane. It photographed ancient river valleys and lake sediments, building a detailed picture of what Gale Crater looked like when it held a large lake billions of years ago, when water filled the crater and Mount Sharp was an island. One charming capability Curiosity has is the ability to take selfies, to photograph itself against Martian landscapes. Using a camera on the end of its robotic arm, the rover can take multiple pictures of itself from different angles, which are then stitched together into a single image, creating photographs that feel almost like postcards from another world, like vacation photos sent back across millions of kilometers. In these selfies, you can see the rover's dusty wheels, its mast with cameras perched on top like eyes on stalks, and behind it, the desolate beauty of Mars. Layered rocks telling stories of water and wind, distant mountains rising into the thin atmosphere, a sky that shifts from butterscotch to blue depending on the time of day and atmospheric conditions. Curiosity also brought music to Mars in a sense. The rover's laser instrument makes a rhythmic zapping sound when it fires at rocks, vaporizing tiny amounts of material for analysis. And engineers programmed it to play Happy Birthday to itself on the anniversary of its landing, creating a brief interplanetary concert for an audience of one. A moment of whimsy in the serious business of planetary exploration. As of now, over a decade after landing, over 12 years, Curiosity continues exploring. It has driven more than 30 kilometers, drilled dozens of samples, and sent back hundreds of thousands of images. It climbs higher up Mount Sharp, reading the geological record like pages in a book, searching for organic molecules and minerals that might preserve signs of ancient life, and teaching us about how Mars evolved over time, how it transformed from a world with lakes and rivers into the frozen desert we see today. On July 30th, 2020, in the middle of a global pandemic, when the world was struggling with disease and uncertainty, NASA launched its most ambitious Mars rover yet, a beacon of hope and achievement in dark times. Named Perseverance, this rover is nearly identical in size to Curiosity, using the same basic chassis and landing system, but carries a different suite of instruments focused on astrobiology, the search for signs of ancient life. It also carried something unprecedented, something that would capture imaginations around the world: a helicopter. Perseverance landed in Jezero crater on February 18, 2021, using the sky crane system that had worked so well for Curiosity. Jezero is special because orbital images show clear evidence of an ancient river delta, where a river once emptied into a lake. Deltas are excellent places to look for preserved signs of life because they rapidly bury organic materials in sediment, protecting them from radiation and oxidation that would destroy them on the exposed surface. If life ever existed on Mars, deltas are good places to look for its fossilized remains. The landing, using the same sky crane technology as Curiosity, but with improved navigation systems, was the most precise yet. Perseverance touched down within 5 meters of its target point, an incredible feat of navigation across millions of kilometers of space, the equivalent of shooting an arrow from New York to Los Angeles and hitting a target the size of a car. And shortly after landing, it began its primary mission, collecting samples of Martian rocks and soil, carefully selecting the most scientifically interesting specimens using its sophisticated instruments, sealing them in special tubes, and storing them for a future mission that would retrieve them and bring them back to Earth. This sample return mission is still being planned, with various agencies working out the complex details, but the goal is to eventually bring these carefully selected pieces of Mars back to Earth, where they can be analyzed with the full power of terrestrial laboratories. Some questions about whether ancient life existed on Mars can only be answered by studying samples in detail, using instruments too large and too complex to send to Mars, using techniques that require careful preparation and analysis in controlled laboratory conditions. So far, Perseverance has collected more than 20 samples from various locations around Jezero crater. Some come from igneous rocks, formed from ancient lava flows that solidified billions of years ago. Others come from sedimentary rocks, deposited by water, layers of material that settled out of lakes or rivers. One particular sample, nicknamed Chayava Falls after a waterfall in the Grand Canyon, has generated enormous excitement among scientists. This rock contains tiny spots enriched with iron phosphate and iron sulfide, minerals that on Earth are often produced by microorganisms consuming organic matter, by bacteria processing nutrients. The rock also contains organic molecules, carbon-based compounds that could be biological or could have formed through chemistry alone. Could this be evidence of ancient life? It's possible, but it's also possible these features formed through non-biological processes, through unusual chemistry in the ancient Martian environment. That's exactly why we need to bring the sample back to Earth for detailed analysis, to study it with instruments that can distinguish between biological and non-biological origins. Perseverance has also made other discoveries that add to our understanding of ancient Mars. It found ancient beaches with wave ripples preserved in rock, tiny undulations that formed as wind-driven water lapped back and forth, showing that Jezero crater once held a shallow lake open to the Martian air, not covered by ice. These ripples are among the clearest evidence yet for liquid water on ancient Mars. It discovered meteorites lying on the surface, pieces of asteroids that crashed into Mars and have been sitting there ever since, slowly weathering in the thin atmosphere. And it has been documenting the geology of Jezero in extraordinary detail, building a timeline of how water came and went in cycles over millions of years, how the climate changed, how the environment evolved. But perhaps the most delightful aspect of the Perseverance mission is its traveling companion, the small helicopter that rode to Mars attached to the rover's belly. Strapped to Perseverance's underside during launch and landing was a small helicopter named Ingenuity, a name that reflects both the cleverness required to design it and the innovation it represents. Weighing less than 2 kilograms and standing about half a meter tall, about the size of a tissue box with rotors, Ingenuity was a technology demonstration designed to prove that powered, controlled flight was possible in Mars's incredibly thin atmosphere. To show that aerial exploration of Mars wasn't just theoretically possible, but practically achievable. Mars's atmosphere is about 1% the density of Earth's, 1/100th as thick. That's roughly equivalent to flying at an altitude of 34,000 meters on Earth, far above where any helicopter has ever operated, far above where the air is thick enough for conventional flight. To generate enough lift in that tenuous air, Ingenuity's blades had to spin at about 2,400 rotations per minute, far faster than helicopter blades on Earth, creating enough thrust to overcome Mars's gravity despite the thin atmosphere. No one was entirely sure it would work. The team planned for 5 test flights over 30 days, just to prove the concept, to demonstrate that it could be done. The first flight was scheduled for April 19th, 2021, a date that would become historic. On that day, Ingenuity spun up its rotors, the blades becoming a blur, lifted off the Martian surface, hovered for 39 seconds at a height of about 3 meters, then landed safely. It was a Wright brothers moment, except on another planet, the first powered, controlled flight anywhere beyond Earth. 117 years after the first powered flight on Earth, after Orville Wright's 12-second hop at Kitty Hawk in 1903, humans had achieved powered flight on Mars, had proven that the sky is not the limit, that flight is possible on other worlds. But that 39-second hover was just the beginning of an extraordinary journey. Ingenuity flew again a few days later, this time traveling laterally, testing its ability to move from one spot to another, demonstrating that it could navigate, not just hover in place. Then it flew higher, faster, further. Each flight pushed the boundaries of what this little helicopter could do, tested new capabilities, explored new limits, and every time it exceeded expectations, performing better than the engineers dared hope. After the initial 5 test flights, after the technology demonstration was complete, NASA extended Ingenuity's mission, transitioning it from a technology demonstration to an operational role. The helicopter began scouting ahead for Perseverance, identifying interesting rock formations and potential hazards, serving as an aerial pathfinder for the rover, showing which routes were passable and which areas deserved closer study. It could cover in minutes distances that would take the rover days to traverse, providing a new perspective on the Martian landscape. Ingenuity flew 72 times over nearly 3 years. 72 flights, each one a small miracle, each one defying the odds. It reached altitudes of 24 meters and speeds of over 20 kilometers per hour, faster than any rover could travel. Its longest single flight covered 705 meters, over half a kilometer traversed in just a few minutes. It operated through dust storms that could have grounded it permanently, through temperature swings of over 100 degrees Celsius between the cold Martian night and the warmer but still chilly day. It survived periods where dust covered its solar panels, threatening to drain its batteries before they could recharge when the sun returned. The helicopter's final flight occurred on January 18, 2024. During landing, one or more rotor blades struck the ground and broke, perhaps due to a navigation error, perhaps due to difficult terrain. Ingenuity sent back an image showing the shadow of a damaged blade, a poignant final message, then settled into its final resting place on the Martian surface. Its mission complete, but its legacy assured. But what a mission it was! What an achievement! Ingenuity proved that aerial exploration of Mars is not just possible, but incredibly valuable. That helicopters can survive and thrive in the Martian environment, despite the thin atmosphere and temperature extremes. Future missions are already being designed based on what Ingenuity taught us, including proposals for larger helicopters that could carry scientific instruments, collect samples from places too dangerous for rovers, or explore areas too rough for rovers to reach, like crater walls or steep canyon sides. One of Perseverance's lesser-known features, easily overlooked amid all the other instruments, is a pair of microphones. For the first time in the history of Mars exploration, we could actually hear Mars, could listen to the wind and the sounds of the rover itself. And it sounds different from Earth, as you might expect. The speed of sound on Mars is slower than on Earth because of the thin atmosphere and its composition. Mostly carbon dioxide rather than nitrogen and oxygen. High-pitched sounds are particularly muted, absorbed by the thin air. If you were standing on Mars and someone spoke to you from a few meters away, their voice would sound quieter and more muffled than on Earth, harder to understand. Birds, if they could somehow survive there, would be nearly impossible to hear, their songs absorbed by the atmosphere. The microphones have captured the sound of wind rustling across the surface, a soft whisper, rather than the howl you might expect. They've recorded the crack of Perseverance's laser zapping rocks, a sharp snap followed by silence. They've captured the crunch of the rover's wheels on gravel, the mechanical sounds of the rover's systems operating, and, most surprisingly, most wonderfully, they recorded the whir of Ingenuity's rotors during flight, a sound like a distant drone, faint because of the thin atmosphere, but unmistakable. That last one is extraordinary when you think about it. The sound of a helicopter flying on another planet, captured and transmitted across space so we could listen to it here on Earth. A sound no human has heard in person, but that we can experience thanks to robotic exploration. These sounds might seem like a curiosity, a nice addition, but not scientifically important. But they're actually valuable. By analyzing how sound travels through Mars's atmosphere, by studying how different frequencies propagate or are absorbed, scientists can learn about atmospheric density, temperature, and turbulence. Sound becomes another tool for understanding the Martian environment, another way of probing the planet's atmosphere and weather. While rovers and helicopters explore Mars ground level, moving slowly across the surface, examining rocks and taking samples, orbiters continue mapping the planet from above, circling every few hours, watching the whole planet systematically. And what they reveal is a world of staggering geological features, landscapes that dwarf anything on Earth, features on a scale that's hard to comprehend. Olympus Mons, the largest volcano in the solar system, is so massive it defies easy comprehension, requires comparisons and metaphors to grasp. It rises approximately 22 kilometers above the surrounding plains, 2.5 times the height of Mount Everest measured from sea level. But unlike Everest, which is a mountain in a mountain range, part of a larger geological feature, Olympus Mons is a single volcano, a shield volcano similar to those in Hawaii, but incomparably larger, standing alone on the Martian plains. The volcano covers an area roughly the size of Italy or the Philippines, about 300,000 square kilometers. Its base is ringed by cliffs up to 8 kilometers high in places, sheer escarpments that make it impossible to approach the summit gradually. You'd have to scale a cliff face taller than any mountain on Earth just to reach the lower slopes of the main volcano, just to get onto the shield itself. The summit has multiple calderas, collapsed craters where magma chambers emptied and the ground above subsided, creating a complex of overlapping depressions. Why is Olympus Mons so huge when Earth's volcanoes are much smaller? The answer lies in Mars's geology and the differences between the two planets. On Earth, tectonic plates slowly move across the planet's surface, driven by convection in the mantle. When a volcano forms over a hot spot in the mantle, a place where magma rises toward the surface, the plate gradually carries the volcano away from the hot spot, and a new volcano forms over it. This is why Hawaii is a chain of islands rather than one massive mountain, each island a volcano that formed over the same hotspot at different times as the Pacific plate moved. But Mars either doesn't have active plate tectonics, or they work very differently from Earth's. The crust appears to be a single piece, or at most two large sections, not the dozen or so plates that make up Earth's surface. So, when Olympus Mons formed over a hotspot, it stayed there, didn't move away. The volcano erupted repeatedly over billions of years, building higher and higher, adding layer upon layer of lava, growing to this colossal size because nothing carried it away from its magma source. The volcano may have been active as recently as 25 million years ago, based on crater counts and other age-dating techniques. Geologically, that's incredibly recent, yesterday in the timeline of the solar system. It suggests Mars might still have volcanic potential, might still have molten rock beneath its surface, though we've never observed an active eruption, never seen lava flowing, or ash erupting. The planet appears quiet now, dormant, but perhaps not completely extinct. Near Olympus Mons are three other massive volcanoes: Ascraeus Mons, Pavonis Mons, and Arsia Mons. Together, they form a line across a region called Tharsis, a vast elevated plateau that dominates Mars's western hemisphere. Tharsis itself is about 8 kilometers higher than the surrounding terrain, a massive bulge in the planet's crust that probably formed as magma accumulated beneath the surface billions of years ago, pushing the crust upward. The weight of Tharsis and its volcanoes may have affected Mars's rotation, may have influenced where the planet's poles ended up, may have shaped the planet's overall geography. On the opposite side of the planet from Tharsis lies Hellas Basin, one of the deepest impact craters in the solar system, a scar from an ancient collision so violent it nearly shattered the planet. It's about 9 kilometers deep and over 2,000 kilometers across, created when an asteroid tens or hundreds of kilometers across slammed into Mars billions of years ago. If you were standing on the floor of Hellas Basin, the atmospheric pressure would be noticeably higher than elsewhere on Mars, because there's that much more air above you. The thin Martian atmosphere compressed slightly by the depth of the basin. But the most spectacular feature on Mars, the one that captures imaginations most vividly, is probably Valles Marineris, a canyon system that stretches for over 4,000 kilometers along the Martian equator. That's roughly the width of the United States from New York to California, a distance you could drive for days without seeing both ends. In places, the canyon is 200 kilometers wide and 7 kilometers deep. If you stood on one rim, the opposite rim would be beyond the horizon, lost in the curve of the planet, hidden by Mars's curvature. You couldn't see across even on the clearest day. Valles Marineris wasn't carved by water, despite its enormous scale, and despite the fact that it looks like it could have been a giant river. It formed as the Martian crust fractured and pulled apart, probably due to the stress of the Tharsis bulge forming to the west. The weight of all that volcanic material stretching and breaking the crust. Over billions of years, landslides and erosion have widened and shaped the canyon. Mass wasting events where entire cliff faces collapsed, sending boulders and debris tumbling to the canyon floor. But its fundamental origin is tectonic, a rift where the crust split. Walking along the rim of Valles Marineris and looking down into its depths would be one of the most awe-inspiring experiences imaginable. A view that would stay with you forever. The scale would be overwhelming, the sense of depth dizzying. The silence would be absolute, except for the thin wind sighing through your spacesuit, and the knowledge that you're standing on another world, looking at one of the solar system's grandest.
Geological features would be humbling in the extreme, would make you feel small and fragile, and connected to something larger than yourself. Perhaps the most important discovery about Mars, the one that changed how we think about the planet more than any other, is how much water it once had. We're not talking about isolated puddles or brief floods. We're talking about rivers that flowed for millions of years, carving channels through solid rock, transporting sediment from highlands to lowlands, creating alluvial fans and deltas. We're talking about lakes that persisted for ages, filling crater basins, supporting complex chemistry. We're talking about, possibly, even an ocean that covered much of the northern hemisphere. A body of water that might have been larger than Earth's Mediterranean Sea. The evidence is everywhere once you know how to read it, once you understand what water-carved landscapes look like. River valleys snake across the ancient highlands, merging and branching like terrestrial river systems, following the same patterns that water follows everywhere, governed by gravity and erosion. These valleys are ancient, dating back over 3.5 billion years to Mars's Noachian period. But their morphology clearly shows they were carved by flowing water, not wind or lava or any other process. Delta formations, where rivers emptied into standing bodies of water, are preserved in multiple craters. Jezero crater, where Perseverance is exploring, has one of the best preserved deltas, showing clear layering that indicates sediments were deposited gradually over long periods as water carried material into the crater lake. The sediments show that the delta built up layer by layer, that the process took time, that water flowed persistently rather than briefly. Mineral deposits tell the same story, providing chemical evidence to complement the geological evidence. Certain minerals only form in the presence of liquid water, requiring aqueous processes to crystallize. Clay minerals form when rocks interact with water over long periods. Carbonates form in standing water where carbon dioxide dissolves. Sulfates form when water evaporates, leaving mineral deposits behind. All of these have been detected on Mars, often in ancient terrains, showing that water was present and active in Mars's past. Their distribution suggests that different areas had different water chemistries, some neutral, some acidic, some salty. The diversity is encouraging for astrobiology because it means Mars had varied environments where different types of life might have emerged or thrived, environments with different chemical conditions that could support different metabolisms. But here's the mystery that drives much of Mars research. Mars today is cold and dry, with an atmosphere so thin that liquid water can't exist on the surface under normal conditions. Water ice exists at the poles and underground, but liquid water, which is essential for life as we know it, can't persist on the surface. The atmospheric pressure is too low and the temperature is too cold. Water exposed to the Martian atmosphere would quickly freeze or sublime directly from ice to vapor. So what happened? Where did all that water go? How did Mars transform from a world with rivers and lakes into the frozen desert we see today? Some of the water is still on Mars, frozen in the polar ice caps and as ground ice beneath the surface. Mars has a lot of subsurface ice, especially at high latitudes, just beneath the surface. Radar instruments on orbiters have detected vast deposits of buried ice, sometimes covered by just a meter or two of soil, sometimes extending deep underground. This ice represents a resource for future human explorers, water that could be melted and purified. But it also represents water that once was in Mars's atmosphere and on its surface. Some of the water escaped into space, molecule by molecule, over billions of years. Mars's gravity is weaker than Earth's, only about 38% as strong, and without a strong magnetic field to protect its atmosphere from the solar wind, charged particles from the Sun gradually stripped away the upper atmosphere over billions of years. As the atmosphere thinned, temperatures dropped because there wasn't enough greenhouse effect to trap heat, and liquid water could no longer exist on the surface. Water that didn't freeze into the ground gradually evaporated and was lost to space, hydrogen atoms escaping Mars's gravity and drifting away into interplanetary space. This process wasn't sudden, didn't happen overnight or even over thousands of years. Mars didn't go from Earth-like to desert overnight. The transition took hundreds of millions or even billions of years. There were probably periods when water flowed again temporarily, perhaps when asteroid impacts or volcanic eruptions released greenhouse gases that warmed the atmosphere briefly, allowing ice to melt and water to flow. For centuries or millennia before conditions reverted to the cold, dry state, the geological record shows evidence of multiple wet and dry cycles, of water coming and going, of climate oscillating rather than changing in one direction. Today, Mars occasionally sees small amounts of liquid water, but only in very specific circumstances, only under special conditions. Salty brines can remain liquid at temperatures below water's normal freezing point, because salt lowers the freezing point. And there's evidence that these brines might flow down crater slopes during the warmest parts of summer, creating dark streaks that appear and disappear seasonally. But these flows are small, temporary, and very different from the rivers and lakes that once existed, more like seeps than streams. Understanding how Mars lost its water and atmosphere is important for understanding planetary habitability in general, for understanding what makes a planet able to support life over long periods. If we can figure out exactly what happened to Mars, why it changed from potentially habitable to inhospitable, we'll have a better sense of how common habitable worlds are, and how stable those conditions need to be for life to emerge and persist. The question isn't just about Mars. It's about understanding the factors that make planets habitable or uninhabitable. Every Mars mission, in one way or another, is part of the search for life, part of the great quest to answer one of humanity's deepest questions. Are we alone? Not little green men or microbes crawling around today, but evidence that life once existed on Mars billions of years ago, when the planet was warmer and wetter, when conditions were more favorable. Why focus on ancient life rather than current life? Because Mars's surface today is harsh, unforgiving. It's bombarded with ultraviolet radiation because there's no ozone layer to block it. The soil contains perchlorates, oxidizing chemicals that would destroy organic molecules. The temperature fluctuates wildly, creating thermal stresses. It's not impossible that microbes exist somewhere on Mars today, perhaps deep underground, where conditions are more stable, where water might exist in liquid form, where radiation doesn't penetrate. But the surface is not hospitable to life as we know it. However, ancient Mars was different, dramatically different. 3 to 4 billion years ago, when water flowed across the surface and the atmosphere was thicker, when greenhouse gases kept the planet warm enough for liquid water, conditions might have been suitable for life to emerge, for simple organisms to develop and spread. If it did, evidence of that life might be preserved in rocks, especially sedimentary rocks that formed in water, rocks that could have captured and preserved the remains of ancient microorganisms. On Earth, we find microbial fossils in rocks over 3.5 billion years old. Simple structures that show where bacteria once lived. Layers of mineral deposits created by bacterial mats. These fossils are microscopic, often just traces of cell walls or chemical signatures left by metabolic processes. But they're detectable with the right instruments and careful examination. Mars might have similar fossils preserved in its ancient rocks, if life ever existed there. That's what rovers like Perseverance are searching for. Biosignatures, patterns or chemicals that are hard to explain without biology, that point to life processes. Organic molecules preserved in rocks could be biosignatures if they show patterns that are more easily explained by biology than by chemistry alone. Certain mineral arrangements, like the layered structures created by bacterial mats, could indicate ancient life. Ratios of chemical elements, particularly isotope ratios that biology tends to alter in characteristic ways, could be evidence of life. All of these are things rovers can look for, measurements they can make, data they can collect. The challenge is that many potential biosignatures can also be created by non-biological processes, by chemistry alone, without any life being involved. Organic molecules can form through chemistry alone, through reactions between carbon dioxide, water, and minerals heated by volcanic activity. Mineral patterns can result from geochemistry, from the way minerals crystallize and arrange themselves without any biological influence. That's why bringing samples back to Earth is so important, why Perseverance is carefully collecting the most promising samples. Only by studying them in detail with sophisticated instruments, with techniques that require careful preparation and multiple lines of evidence, can we hope to distinguish between biological and non-biological origins with confidence. Some scientists think we might have already found potential biosignatures, but can't confirm them without better analysis, without bringing samples back to Earth. The leopard spots in the Cheava Falls sample that Perseverance collected are a perfect example. They look promising, showing minerals and structures that on Earth are often associated with microbial metabolism, with bacteria processing nutrients and creating mineral deposits. But we can't be sure until we get the sample into a laboratory, until we can section it and examine it under microscopes, until we can analyze its chemistry in detail, until we can rule out non-biological explanations one by one. Finding evidence of life on Mars, even ancient extinct life, even simple bacteria that lived billions of years ago and left only the faintest traces, would be one of humanity's greatest discoveries, comparable to the Copernican revolution or the discovery of evolution. It would tell us that life is not unique to Earth, that given the right conditions, it can emerge elsewhere, that we are not alone in the universe, even if we're alone in the solar system now. It would suggest that the universe might be teeming with life, that wherever conditions are suitable, life finds a way. And it would fundamentally change how we see our place in the cosmos, our significance, our connection to the rest of the universe. While this journey tonight has focused mainly on American missions, on NASA's exploration of Mars, Mars exploration is increasingly an international endeavor, a global effort. Multiple nations have sent spacecraft to Mars, each contributing to our collective understanding, each bringing unique perspectives and capabilities. The European Space Agency has had several successful missions. Mars Express, which has been orbiting Mars since 2003, carries a radar instrument that detected subsurface water ice and studied the atmosphere's composition. The Trace Gas Orbiter, part of the ExoMars program, is studying methane and other trace gases in Mars's atmosphere, trying to understand their sources, whether they come from geology or possibly biology. India's Mars Orbiter mission, also called Mangalyaan, reached Mars in 2014 on the first attempt, making India the first nation to succeed on its first try, a remarkable achievement. The orbiter studies the atmosphere and surface, contributing valuable data to the global effort to understand Mars, all at a fraction of the cost of comparable missions. The United Arab Emirates Hope Orbiter, which arrived in 2021, is providing a global view of Martian weather, studying how conditions change throughout the day and across different seasons, building up a comprehensive picture of Mars's climate system. China has rapidly emerged as a major player in Mars exploration. The Tianwen-1 mission, launched in 2020, included an orbiter and a rover named Zhurong. The rover successfully landed and explored the Martian surface for several months, analyzing rocks and studying the soil before entering hibernation. Japan is planning the Martian moon's exploration mission, which will visit Mars's two small moons, Phobos and Deimos, and return samples to Earth. These moons are scientifically interesting because we're not entirely sure how they formed or what they're made of, whether they're captured asteroids or formed from Mars itself in some way. This international collaboration benefits everyone, strengthens the science. Mars is large and complex, and studying it requires observations from many angles, both literally and figuratively. When orbiters from different nations share data, when scientists from around the world analyze samples and publish findings, when engineers collaborate on mission design, we all learn more than any single nation could accomplish alone. The exploration of Mars is a human endeavor, not just an American or European or Asian one. The pace of Mars exploration is accelerating, with more missions planned in the coming decade than in any previous era. Future missions are already in various stages of planning and development. NASA and the European Space Agency are working on the Mars Sample Return Campaign, a complex multi-spacecraft effort that would retrieve the samples that Perseverance is collecting and bring them back to Earth for analysis. This incredibly ambitious mission would involve multiple spacecraft working in coordination. A lander to touch down near Perseverance, a rocket to launch from Mars's surface carrying the samples, an orbiter to capture the samples in Mars orbit, and finally, a return vehicle to bring them safely to Earth. It's the most complex planetary mission ever attempted. There's also increasing discussion of human missions to Mars, of sending astronauts to walk on the red planet. NASA has stated a goal of landing humans on Mars by the 2030s. Such a mission would be the culmination of decades of robotic exploration, using everything we've learned about Mars's environment, resources, and challenges to make human exploration possible. A human mission to Mars would be far more complex than the Apollo moon landings, orders of magnitude more difficult. The journey alone would take 6 to 9 months each way, depending on the alignment of Earth and Mars, compared to 3 days to the Moon. Astronauts would need to be largely self-sufficient for the 2 to 3 years the mission would last, including the time spent on the Martian surface, waiting for Earth and Mars to align properly for the return journey. They'd need to produce their own water from ice, generate their own oxygen from the atmosphere, possibly even make their own fuel for the return journey using local resources. It's a daunting challenge, but not an impossible one. The challenges, while daunting, appear to be solvable with current and near-future technology. We know Mars has abundant water ice that could be melted and purified for drinking and other uses. We've demonstrated with the MOXIE experiment on Perseverance that we can produce oxygen from Mars's carbon dioxide atmosphere, splitting CO2 into carbon and oxygen using electricity. We've tested new spacesuit materials in the harsh Martian environment, learning how they degrade and how to make them more durable. We've learned how to land large payloads with precision using the Sky Crane system. Each robotic mission brings us closer to the day when the first human will step onto the rusty soil of Mars and look around at a landscape shaped by billions of years of wind, water, and time. What will those first explorers find? Perhaps evidence of ancient life preserved in rocks they can carefully extract and study. Samples they can examine with human eyes and human judgment, rather than relying on robotic instruments. Perhaps clues about Mars's early history that no robot could recognize. Subtle features that require a geologist's trained eye to interpret. Perhaps simply the profound experience of standing on another world, looking up at a sky where Earth appears as a pale blue dot, and feeling the weight of that accomplishment. The significance of being the first of our species to walk on another planet. There's something deeply meditative about Mars exploration, something that invites patience and reflection. The rovers move slowly, typically traveling no more than a few hundred meters in a day, often much less. Sometimes just a few meters when the terrain is difficult or when they need to study something carefully. They stop frequently to examine rocks, to take measurements, to photograph their surroundings from multiple angles. Communication with Earth takes between 5 and 20 minutes each way, depending on where Mars and Earth are in their orbits, depending on the distance between the planets. So everything happens at a deliberate pace. So commands must be planned carefully and sent in advance. The rovers operate semi-autonomously during the Martian day, following general instructions, but making detailed decisions themselves, then reporting back what they accomplished. The orbiters circle Mars every few hours, each orbit offering a new perspective, new lighting conditions, new opportunities to observe phenomena like dust storms or frost formation or clouds drifting through the thin atmosphere. Over years and decades, they build up comprehensive data sets showing how Mars changes with seasons, how different regions respond to temperature shifts, how dust is transported around the planet by winds, how the polar caps grow and shrink with the cycle of the year. This patience is necessary, imposed by physics and distance. Space is vast, Mars is far away, and good science takes time. But there's also something beautiful about this enforced patience, something valuable in the slow, steady accumulation of knowledge. In a world of instant gratification and rapid news cycles, Mars exploration reminds us that some things can't and shouldn't be rushed, that understanding takes time, that knowledge is built brick by brick through careful observation and analysis over years and decades. The rovers embody this patience perfectly. Curiosity has been exploring for over a decade and has traveled only about 30 kilometers in all that time, an average of less than 10 meters per day. But in those 30 kilometers, it has read billions of years of history, identified environments where life could have thrived, discovered organic molecules and unexpected minerals, and taught us more about Mars than centuries of telescopic observation ever could. The slow pace isn't a limitation, it's a feature, allowing careful study rather than rushing past interesting features. Perseverance is just beginning its journey, methodically selecting samples that might answer one of humanity's deepest questions. Are we alone? It might take a decade before those samples reach Earth. Longer than many people's attention spans, longer than we'd like to wait. It might take longer to fully analyze them, to run all the tests, to examine them from every angle, to reach confident conclusions. But the answer, whatever it turns out to be, will have been worth the wait, will justify the decades of effort and patience. As we drift toward the end of our journey tonight, As our time together draws gently to a close, let's imagine Mars as it is right now, in this very moment. It's afternoon on the Jezero crater floor where Perseverance sits. The rover quiet as it processes data from the morning's work. The sun, smaller and dimmer than it appears from Earth, about 2/3 the size, tracks across a butterscotch sky tinged with suspended dust. Shadows stretch long from the rover's wheels, creating patterns on the rust-colored ground. Somewhere above, hidden from view by the glare of daylight, Earth hangs in the Martian sky, a bright blue-white point of light, accompanied by its pale companion, the Moon, both visible as a single bright star in the Martian sky. The wind, such as it is in the thin atmosphere, rustles past the rover's instruments, making a sound that the microphones can barely detect. A whisper so soft it's almost inaudible. Dust devils spin in the distance, narrow columns of dust lifted by convection currents, mini tornadoes that dance across the ancient river delta, following paths dictated by temperature gradients and local topography. Ephemeral sculptures shaped by Martian air, appearing and disappearing as the surface heats and cools. In a crater somewhere else on Mars, perhaps Spirit still sits where it became stuck over a decade ago. Its solar panels probably covered in dust by now, its instruments silent and cold, but still intact. Nearby Opportunity rests too, its final resting place unmarked except by the tracks it left in the soil, slowly being covered by wind-blown dust. These rovers gave us years of discovery, exceeded all expectations, and now they've become part of the landscape they explored, monuments to human curiosity and robotic perseverance. Ingenuity lies still as well, its rotor blades damaged, but its legacy intact, its mission complete, but its influence continuing. That little helicopter proved that the sky is not a limit, even on worlds with barely any sky at all. Future aerial explorers will follow the path it pioneered, flying where rovers cannot roll, exploring cliffs and canyons that are too steep for wheeled vehicles. High above, orbiters continue their silent vigil, cameras pointed down, radars piercing the surface looking for subsurface ice, spectrometers analyzing the atmosphere's composition. They map and measure, patient sentinels watching over a planet that has no permanent residents except robots and the occasional meteorite. A planet that exists in quiet solitude, except when we send our emissaries to visit and learn. Mars doesn't care about our explorations, of course. It's indifferent to our curiosity. It spins and orbits as it has for billions of years, its seasons coming and going according to the laws of physics, its dust storms rising and falling with the changing temperature, its ice caps growing in winter and shrinking in summer. It existed long before we looked up and saw a red point of light in our sky, and it will exist long after humans have either colonized it or moved on to other destinations, or possibly ceased to exist entirely. Mars will remain patient and timeless. But for now, in this brief moment of cosmic time, Mars and Earth are connected by radio waves and shared curiosity, by the signals that travel between the planets, carrying commands one way and data the other. We send our robotic emissaries across the gulf of space to touch another world and bring back stories. And Mars, in its way, responds, revealing secrets held for eons, showing us what it was like when water flowed and perhaps life stirred in ancient pools, opening itself to our study. So, dear viewer, dear companion on this journey, wherever you are tonight, whatever time zone you're in, whatever brought you to this video, whether you found it intentionally or stumbled upon it while searching for something to help you sleep, I hope you found some peace in our journey to Mars. We've traveled far in thought, visiting a cold desert world that whispers of warmer days long past. A world that holds secrets about how planets evolve, whether life is common or rare, what makes a world habitable or inhospitable. We've met the rovers and orbiters and helicopters that serve as our eyes and hands on that distant shore. The robotic explorers that work tirelessly without complaint, that persist despite difficulties, that exceed our expectations again and again. We've seen towering volcanoes that touch the edge of space, and vast canyons that could swallow continents. Evidence of water that once flowed freely, and hints of possible life that may have emerged in ancient lakes. Mars reminds us that planets are not static stages, but dynamic worlds with their own histories, their own stories of change and evolution, their own character and personality. It shows us that Earth is not the only place where water has flowed and conditions have been suitable for life, that the cosmos offers many opportunities for complexity and perhaps biology. And it invites us, through patient exploration, to uncover mysteries that no human has ever witnessed. To read the record written in rocks and minerals, to listen to the whispers of ancient rivers and vanished seas. The exploration of Mars is far from over, is in fact just beginning. In fact, in many ways, we're still in the early stages of understanding this neighboring world. Each mission builds on the discoveries of those before it, asking deeper questions, searching with better tools, venturing into new terrain, pushing the boundaries of what's possible. The samples that Perseverance is carefully collecting might one day tell us whether we are truly alone in the universe, or whether life, in some form, has stirred on other worlds beyond Earth. That would be a discovery of profound significance, one that would echo through human culture and philosophy. But those answers will come in time, with patience, with continued dedication to careful science and daring engineering, with the sustained effort of thousands of people working together toward a common goal. For now, we can rest in the knowledge that somewhere out there, right now, rovers are rolling across the Martian surface, orbiters are watching from above, and Mars is slowly, steadily revealing itself to us, sharing its secrets with those patient enough to listen, generous enough to wonder. You have explored enough for tonight. You've done more than enough. Your curiosity has carried you across millions of kilometers to visit another world. Your imagination has walked on rusty plains and looked up at distant mountains, has stood at the rim of the largest volcano in the solar system, has peered into canyons deeper than any on Earth. You have witnessed some of humanity's greatest achievements in robotic exploration and contemplated questions that reach to the heart of what it means to be alive in this vast cosmos, to be conscious beings wondering about our place in the universe. Now it's time to rest. Close your eyes and let the images of Mars gently recede, like memories of a dream slowly fading. The dusty plains, the layered rocks telling stories billions of years old, the thin wind sighing across ancient channels, the butterscotch sky hanging over a frozen desert. Let them become dreams if they wish, or simply fade into the soft darkness behind your eyelids, releasing their hold on your conscious mind. Mars will still be there tomorrow, still spinning in its orbit around the sun, still holding its secrets close. The rovers will continue their patient work, operating according to their programmed instructions, examining rocks and soil with tireless dedication. The orbiters will keep their tireless watch, mapping and measuring, building datasets that will be analyzed for years. And somewhere in the planning stages, in laboratories and design centers around the world, the next mission is taking shape, preparing to add new chapters to the story we've been writing together since Mariner 4 first flew past the red planet in 1965. You've done enough for today. You've traveled farther than most people ever will, if only in mind and spirit. You've learned much, honored the spirit of exploration that lives in every human heart, connected with something larger than yourself. Rest now. Let sleep come gently if it will. Dream of distant horizons if you'd like, of rovers climbing ancient mountains and helicopters flying through thin air. Or dream of nothing at all. Either way, know that you are part of this great adventure, part of the species that looked up at a red dot in the night sky and decided to visit, to learn, to understand. From Mars, from Earth, from the space between where radio signals carry our curiosity and discoveries flow back in return. From the past to the present to the future. Good night. Sleep well. Rest deeply. Let the universe cradle you. The stars will keep watch. Mars will wait. And tomorrow, if you wish, you can explore again. But for now, for this quiet moment, let peace settle over you like dust after a storm. Close your eyes, breathe slowly, and drift gently into sleep, knowing that somewhere out there, on another world, our robots continue their patient work, seeking answers to questions as old as consciousness itself. Good night.